Good afternoon, everyone. For the autonomous watering and fertilization system, let me introduce our team members. Project Manager Peter Chen, Technical Manager Steve Annessa, Maitram Nguyen, and I'm Sunny Joshi. First, we'll go over the problem statement. An amateur gardener is looking for a device that automatically waters and fertilizes their plants. In order to accomplish this, we created a robot that moves by itself using computer vision, detects moisture of plants, can spray water and fertilizer when necessary. Something like that. Now, there were some objectives to our project. To develop an autonomous device that will maintain plant growth and life. Focus on modularization and scalability as the primary targets, and the product should be reprogrammable with an open architecture. The requirements placed on our project were we have to have a 3-gallon water tank, 1-gallon fertilizer tank. The runtime for the project should be long enough to water 30 plants, which is approximately 2 hours. Should be able to detect moisture level and should be easy to configure. This is the top-level design of our. The user provides plant location, required moisture. The robot then moves to the plant location, detects plant moisture, and applies water and fertilizer as necessary. This is the system architecture. Since we are using a robot that uses computer vision, we needed a camera, an OpenCV software to do image processing, and a processor that can do fast enough real-time image processing. We chose the ASUS ePC network to do that. The ASUS is connected to the Arduino through an Ethernet shield. The Arduino is like the core of our, it's a microcontroller, and it controls all the pumps for motion, water pumps and fertilizer pump to spray water and fertilizer. It also controls the sonar sensors that are located in the front and back of the robot, and it also controls the 2 linear actuators. The first linear actuator is used to pull the hoses in and out to spray water and fertilizer, while the other one is used to push the moisture sensor in the soil. Now, since we have this, we needed a user interface for the user to interact with the robot. So we created a Java app that allowed the user to input data like moisture and plant location. Now we have the number of plants that are in the system and the moisture and plant location. So now we need to move to the next step is to move to the plant. In order to do so, we created custom labels and placed it on pots. Now Maitram will go over detecting labels and how to use them.
In order to detect objects and its location, we will detect label detection software by using OpenCV library. This is the flow of image processing. So the image color is captured from the camera and then run through color thresholding, edge detection, shape recognition, and size classification. And next, we design a label. We chose black and white color because they have high contrast to enhance edge detection. Rectangle outside and triangle inside. We use binary encoding to describe different sizes. Black for 1 and white 0. The leftmost triangle is the most significant bit. We have label. Now we recognize it. So first thing, we convert color image into black and white. And the edge detection, we identify the border between black and white. By lighting the image, we reduce noise and enhance all the edges. And next, we decode the image. And finally, we find the center and the area of the label. And now the label tracking. So by knowing the center of the label, we use the x-axis value to track the label. So to move a robot, we try to keep the label in the center of the camera. So if the x value below than 281, we move to the right. And if the x value above the 259, we move to the left. Otherwise, we move forward.
Okay, so we know our plants, we know how to find them. We actually have to use something to move to them. So we had to construct a robot base. Unfortunately, we couldn't buy one because of the requirements in the project. The weight and cost was not feasible. We started off with two 26-inch aluminum bars spaced 10 inches apart. Those are here to here. There are 5 cross-sectional steel bars that connect the load supporting wheels. That's these 5 bars going that way, horizontal. And the load supporting wheels do 2 things. The first thing they do is distribute all of the weight on the track. The second thing they do is keep the track in place. When you turn a track system, it tries to jump off the wheels. There's tabs inside of the tracks the wheels go through to make sure that they're always in contact. You see, if you go to the back, there's 2 sprockets here, 2 sprockets here, and 2 sprockets there and there. They connect the entire thing together and create a stable pump. Now, we have many components. We could either have built out and made the system very wide, or built up like we did. We built up. This allowed us to work in a grid-like pattern that you might find on a farm. So, we needed at least 3 layers. Each layer has 26 by 14 inches of usable space. In order to keep these layers tight and structurally sound, we had to connect them at 8 points at the front, sides, and rear, which you can see over there. On the bottom layer, we have our battery and fertilizer tank. The battery is the heaviest item. The second heaviest item is our water tank. We placed this in the middle because we wanted to be able to expand if the requirement came. Our requirement is 3 gallons, but we can hold it up to 10 conveniently in that space. Above all of this is the electronics. These were placed on the above to counteract any event failure from our pumps, hoses, or containers. And we built this to hold 150 pounds, successfully tested it with 250. This is our circuit diagram. You see the Arduino Mega 2560 is connected to our simple H bridges here for movement, H bridges to control our actuators and pumps. We have fuses and a circuit protector. But most importantly, because we have all of these components, we actually had to implement a buffer to move some of the current from sourcing from the microcontroller. Now let's talk about how we move this thing. What's our algorithm? We first start. Then we check for a label if it's within the visible path of the robot. If we find it, we determine if we can move based on the output from our sonar sensor. If our sonar sensor says it's okay, there's nothing in front of it, we have a clear path, we move to the label. We continue this until the label size is an area of 70,000. Once we're there, we know we're at the plant. We check the moisture, which is this actuator right here, that will move down into the plant. We determine if it needs water or fertilizer based on that output, and then we reverse to the left and repeat the process. Now we're going to show you a video of this whole thing in action. You're going to see 3 plants. The first plant will need water, the second plant needs nothing, and the third plant needs fertilizer. As you can see in the front, the blue bulb is water and the red bulb is fertilizer. Those are the labels on the plants. This is live, real-time speed. Moisture sensor going into the soil. You see this actuator coming out. Water's being applied. Actuator's going back. And now we reverse to the left, keeping the image still visible. When the area of the image is sufficiently small, which is less than 1,000, we know we're far enough away and we look for the next label. We found the label, and now we're moving to it. That's what the robot sees. This plant did not need moisture. Now we're going to speed it up a little bit. H-bridge for movement. Now the actuator is coming on again, and fertilizer has been applied. It is liquid. Okay. So it works. Good news. Let's talk about tests. Most importantly, we felt that our accuracy in continuing to measure the same value from our moisture sensor was important. In moderately wet soil, we found an ideal measure to be 495. That number is the value given from an ADD on the microcontroller. It goes from 0 to 1023. We were able to be within 2 deviations of that over 10 trials. For dry soil, we were slightly off with 3 deviations, and that makes sense. The moisture sensor works on the amount of conductivity. With less water, you have less conductivity, you have a bigger shift. But it's okay, it just means the plant needs water either way. In overly wet soil, we were fine, the same as wet soil. Now let's talk about if we vary sunlight and distance, what happens. Sunny at 2 feet, overcast at 2 feet, and dusk at 2 feet, we have 100% over 6 trials of visually seeing the label. As we move back, sunny at 5 feet is 100%, overcast at 5 feet is 80%, and dusk is 40%. We start to see a pattern. If we lose our lighting condition, this becomes less effective. So let's talk about an overall test, because that's the most important thing to go from start to finish. The video you saw was an overall test of just 3 plants. In sunny conditions, over 6 trials, we had 100% accuracy. In overcast conditions, over 6 trials, we had 2 failures, and we attribute this to 2 things. First being lighting. The second being the communication between our PC and Arduino, which Peter will talk about later in the future improvements. As you can see, in dusk, we were not able to complete a full trial. And this is good news, actually. This tells us that we have an operating range. We know we can go after dawn and right before dusk, and we're fine. Now Peter's going to talk about future improvements.
Now our label detection software needs 100% match to find a label. In real world, we found out it's not feasible only in the ideal condition. So we would like to do our label detection software to allow 10% deviation for label matching, so which will improve our overall system. We also would like to use interrupt-based communication between ASUS PC and Arduino. We also want to have shape encoder for our motor as a third feedback for movement. We'd like to create filling and charging station in the future. Here is the component we're using in this project. The total is cost for this project is $2,600. It's a little bit high because our project needs a weight requirement. In order to achieve that, we have to use a bigger motor with gearbox, which draws a lot of currents. So we gotta use a bigger battery, which adds to our weight and cost. Here's the man hour we spend. The total hour for each person, we spend at least 300 hours. Did that because everything we start from scratch. Here we spend at least over 1,000 hours for effective effort. Total development cost of the project is $24,400. Here's the member responsibility. We divided all the tasks and assigned between members equally. While working this project, we've learned a lot. Here's the key point. We learned how to work with steel and aluminum. We know how to design a track-based chassis. We have to deal with the mechanical engineering principle. We do a noise reduction and image processing. We have learned that it's very important to test an individual component for implementation. That already have a plan B. And I would like to give a special thanks to Dr. Nelson and Dr. Economity for faculty supervisor, Kevin Sleevey for editing our video, friends and family, and thank you all for coming.